In this first item on the exam, we've got data from a tension test, both in numerical form as well as in graphical form. Note that the entire test data is showing up on the upper one. Fracture happens way out here at the far right. And then we've got a close-in view over here in the bottom one. And that close-in view ends right where we see this dashed line or very thin line right here. We're asked to find the modulus of elasticity that is estimated from the test data. We're given that we start off with an original diameter of the specimen of a 1/2 inch, and the elongation or deformation information is recorded with a gauge length of 2 inches. Now, when you're working with experimental data, you'd like to try to stay away from the extreme points. That is the 0, 0 because of testing equipment, whether or not is really perfectly calibrated there at 0, 0, and you want to stay away from up here at the top end where we don't exactly know where the proportional limit has begun and ended, or that is the linear elastic region has ended and the nonlinear portion has begun. So what you like to do is actually probably try a variety of different combinations of the stress of the strain values, and it makes sense, for a test maybe, especially if you don't have much time, to just come in one data point in from each end. That's what's circled here. Certainly the proportional limit is no higher than this value right here, and since we got all the data points in numerical values available to us, that's what you see here. So that means that when we want to go estimate what our value for E is based upon our test data, we'll take a range of our stress and divide it by the range of the strain over that particular area or a location of those two data points. Right now, we're not given stress and strain, we're given load and axial deformation, so we have to get that going in here. So we have a load of 9,600 pounds minus 1,600 pounds for those two different data points, and then we'll divide by the area. Since we have originally a 1/2 inch diameter, that would be pi times 0.5 inches squared divided by 4. That'll give us our stress, and then we'll multiply by 1 over our strain. Our strain range is 0.0031 minus 0.00004 inches, and that occurs over the 2-inch gauge. So there's your pounds per square inch over inch of deformation over inch of original length. And when you calculate that out, that will be approximately 30,180 KSI. That's awfully close to typical value for steel, and that's probably reasonable given the stress strain curve profile that we see here, that might be what's going on. So you could estimate here that E is approximately 30,000 KSI. The 180 is sort of debatable here. Certainly, though, we're real close to 30,000.